well. So before we dive into this discussion of the NOPP Coastal Impacts Hurricane Program, I want to start by acknowledging that we're diving into a topic with really high stakes. These extreme weather events are devastating. They cost humanity, on average, some hundreds of billions of dollars a year in damages, thousands of lives lost. And just in this past year, for example, just Helene and Milton, two hurricanes that impacted the eastern coast of the United States, are estimated to have cost close to $200 billion in damages. Millions of families and people had their lives impacted, displaced from their homes, significantly disrupted, and at least hundreds of people lost their lives in these storms. We are very passionate about the science and the technology development. We're very proud of the progress we're making, but the end goal here isn't just understanding, it's not just finding more beautiful math, it is to make a real impact in reducing the harm of these extreme events. The opportunity for that impact today is not to change the course of storms. It is to better understand these systems so that we can more accurately predict exactly where and when they will impact coastlines and how much energy they're going to be depositing and how in the forms of waves and winds and storm surge and flooding. In the past decades, we've made tremendous progress. We have steadily reduced the error in prediction forecasts of storms. We've steadily reduced the lead times at which we're able to make accurate predictions. But there's still a lot of room for improvement. We still have cases where we are hundreds of miles off several days out, and that can impact millions of people. If we can make better predictions, we can do a couple of things. We can make sure that we can focus preventative resources for mitigation where they really should be. We can focus recovery preparation where it really needs to be, getting ready to move into areas and help people that we know are going to be impacted. And we'll gain public trust. We can make the mitigation efforts more reliable, more effective, and less costly. And that will translate to saving lots of dollars, but also saving lives eventually. So how do we actually improve the understanding, the quality of a forecast? There's two key ingredients. One are models, and models are math that are encoded in computers, and you hit play, and the model runs the world forward and makes a prediction of what the state of the world will be somewhere else or somewhere in the future. And so these are really striving to perfectly capture how physics work. The other key ingredient are observations. These are little sparkles, snapshots of perfect truth. To run it forward, we have to have a perfect starting point. And so we use sensing to understand what the initial state of the world is, and then we use models to propagate that state forward. But then there's this recipe where we mix these key ingredients, which is assimilation. It's the process by which we take real sensor data, models, dig into all the messiness. These things are far from the perfect aspiration. And so there's a lot of effort and math and technology development that goes into the process of assimilating, combining observations and models to make our best estimate at what's really going on out there. And it's particularly difficult in storms because they are chaotic systems. And chaotic system, that means that it's difficult to predict its future state. And by difficult, we really just mean that there's not a lot of correlation between initial conditions and future state compared to other systems. If we roll a ball down a hill, we know exactly where it'll be 10 seconds from now, 100 seconds from now, 1,000 seconds from now. Our error might expand gradually, but it's nice and controlled. We can stack up our estimates and make predictions that are far away from our initial starting point. If you start a double pendulum swinging, it very quickly goes into pure chaos unpredictability, where pendulum that might be swinging with a period of 1 second, single perturbations on the scale of atoms will make it completely chaotic and unpredictable next week. that's a lot like what weather systems are for us. But then on top of that, they're complex chaotic systems. And that means that there's lots of different factors. There's air, there's water, there's energy, there's heat exchange, there's processes going on at very small spatial scales, huge spatial scales, global scales of Coriolis effects. And measuring all of that requires lots of different measurements, and modeling all of that requires lots of different kinds of models all working together. And for humans, that means we've got to collaborate. There are too many expert niches required for an individual entity to be able to effectively tackle this challenge. And that is really the genesis of this NOPP program. So NOPP is the National Oceanic Partnership Program. It's partnership between government, academia, and industry, and it is focused on addressing operational challenges in our oceans. One of the largest operational challenges is how do we approach extreme weather? This Hurricane Coastal Impacts project has 10 collaborative teams spanning industry, academia, and government. We have several of those teams here today who are going to talk about the work that we've been doing. And we've been advancing models, advancing sensor deployments, and getting closer to improving operational storm forecast for several years now. And it's very exciting progress, and I'm thrilled to be with this group talking about that today. We have Dr. Jim Thomson, who is a principal oceanographer at the University of Washington's APL and a professor in civil and environmental engineering. He holds a PhD of applied ocean physics from MIT with the Woods Hole Oceanographic program. And Dr. Thomson studies waves and turbulence at the ocean surface interface, so between the atmosphere and the top of the ocean. And his group has developed a SWIFT, it's called a SWIFT sensing buoy platform, which is a very low cost, low size, free drifting sensing platform. We have Dr. Jenna Brown from the US Geological Survey. Dr. Brown specializes in collecting field data to measure extreme storm impacts and recovery. She holds a PhD in oceanography from the Naval Postgraduate School and has been involved in a number of collaborative field experiments with and beyond the NOPP program, applying her expertise to better understand coastal hazards and coastal changes. And then we have Eric Stackpole, who's a mechanical engineer and entrepreneur with a couple decades of experience in marine technology research and development. He started his career in NASA Ames, founded a company called OpenROV, where he pioneered developing a new category of extremely small and affordable underwater remote operated vehicles with the aim of democratizing ocean science. Eric was a founding hardware engineering lead at Sofar Ocean, and also happens to be a TV star in James Cameron's OceanXplorers docuseries, which is an amazing show. You should check it out. I'll plug that for you, Eric. And with that, I'll hand it over to Dr. Jim Thomson. And Jim, just give me a nod when you'd like me to advance slides.
Sure. Thank you, Evan. Thank you all for being here. It's fun to talk about this project. It's been a really successful partnership. We've collected a lot of data and we've all learned a lot, and there's much more coming now that we have so much collected data. So the part of the project that I will tell you about is deploying wave buoys ahead of these storms, trying to have them laid out in an array so that the storm track will go over this array of buoys. I want to give you some ideas of why we would do that, scientifically. The first is that we would like to improve the forecast of the waves that will arrive at the coast. Certainly, if you've ever been standing on the beach on a day when there are big waves, you see that each individual wave can have an enormous impact on a structure, on a pier piling, on a breakwater, on a seawall, anything like that. So you can imagine when you have a large storm with storm surge, those individual waves, they do a lot of damage. The waves also contribute to the storm surge itself. So that just average water level, that elevated water level that happens when a storm makes landfall, waves are one component of that. So we're concerned with sort of flooding in the background sense of mean water level, and then we're concerned with the waves that are one at a time impacting structures and everything at the coast. That's where you hit the coast. But before that, there's also a lot of interest in what the waves are doing for the air-sea exchange. So fundamentally, a hurricane is a heat engine, and it's getting its heat, its source, from the ocean. These warm sea surface temperatures that are out in the Gulf of Mexico and the tropical Atlantic, that's what produces hurricane season. And we want to understand the exchange between that ocean heat and the atmosphere and how that controls the evolution of a hurricane. Will a hurricane rapidly intensify? Will a hurricane just kind of go away? How is it going to evolve? That's all about that coupling. And waves are the interface through which that coupling happens. So there's a reason to be making these measurements even before the hurricanes arrive at the coast. And then the reason to do this particular mode of sampling that we've used in this program, which is very targeted, right? We have been putting out buoys ahead of a storm once we have a forecast of where the track is, rather than just having buoys everywhere. And that's because we've noted from the last 30 or 40 years of hurricane research that if you just have an existing array, something like the NDBC array, that's a national program here, or the CDIP array, or even the Spotter's more recent global drifting array, that's actually not sufficient. As impressive as those arrays are, and having thousands of buoys in the ocean is great, but it's still not enough because the hurricanes can be fairly compact. They're really limited to maybe 100 or 200 kilometers in extent where they're going to make the biggest impact, and you can just miss all of your buoys if you're not lucky. Okay, so here's some images just to walk you through those bullet points. First, that's what the surface of the ocean looks like at the bottom left. During a hurricane, you can see the waves and wave breaking and sea spray are really a big part of how the ocean and atmosphere are talking to each other. Next is a histogram and a quick analysis from Hurricane Ian, one of the storms that we sampled, and a very high damage, really impactful storm. And this is someone working on the project, was also a Coast Guard officer getting his master's degree here at the University of Washington. And he did an analysis of the damage to Coast Guard aids to navigation, the buoys that tell you where to go up a channel, those things. There were thousands of them destroyed during Hurricane Ian. And he did a retrospective analysis to say, well, those ones that were destroyed, what were they most likely destroyed by? Big waves, strong winds, or just flooding, background total water level? And it turns out that waves, high waves, waves over 5 meters, are most associated with the likelihood of having a damaged Coast Guard infrastructure. It's the big waves that really matter. And then the last thing about all of this work is that I just want to point out that planes are fun. That I think that there's been some real challenge, but it also adventure in doing this work. So there's an image with the team putting out a lot of the buoys. Eric's in that image, I'm pretty sure, and so is Jake Davis, a student here who has made huge contributions in this work. And then the rest of the people in that photo are from the VXS-1 squadron. That's a squadron of naval aviators who fly out of Pax River, and they have provided all the air support for this program, and it has been phenomenal working with them. They are real professionals and have really helped us get this work done. So with that, I'll go to the next slide and show you a little bit of what we've done. We have put out 2 different types of buoys. So if you're familiar with Spotter, I'm sure you're familiar with the Spotter buoy, or so far, you're familiar with the Spotter buoy. So that's what's shown on the left here. And these are a commercial product. Thousands of them have been made. They're very well validated, well verified, and they're a great tool for doing this. So we've relied heavily on the Spotter platform. But there's one thing that is a little bit more challenging about the Spotters is they're big enough they have to go out the open door of an airplane. So this is flying in the P3 from that same squadron I just acknowledged. This is what it looks like to toss one of those out the door with the cardboard foil around them that helps them fall correctly in the air and land correctly. And they don't actually have a parachute. They just fall with that cardboard sort of drag element on them. Those have been great, but we've also used the research buoys that we make here in my group, which we call a micro Swift. So it's a miniature version of the Swifts we have been making for a long time. They're sort of a distant cousin to the Spotter buoy in a lot of ways, but they're still very much a research platform. We don't sell them. We never intend to. It's something that we make in-house so that we can do weird things with them and change the sampling and try stuff. It's been a nice partnership between the two. We've been able to try some things that on the micro Swifts that you probably would never do in a commercial product. But we've also been able to do lots of intercomparisons, and things compare and agree really nicely in terms of all the wave measurements and everything. So we've been able to use these two platforms in terms of the data sets as if they're just one data set. So that's been great. One of the key differences about the micro Swifts is it goes out of the tube of the aircraft. So most of these research aircraft, they have a dropson tube that's for deploying lots of different things. Most most commonly it's for the sondes that make atmospheric measurements, but you can also use these tubes to deploy things that end up in the ocean. So there's a picture of me inside the P3 and the tube is open and I'm putting this micro swift, which has got the cylindrical shape wrapped in cardboard. I'm putting it out the tube, and then if you watch the animation below, you'll see what it looks like underneath the aircraft as the buoy comes out of the tube. And there's a small chute that deploys and helps it, to land upright and slows it down a little bit. Although it's still moving pretty fast when it hits the water. There you go. It's coming out right now, and that's what it looks like as it goes out. So part of the partnership here has been to combine a commercial sensing platform with a research one, an academic one, and use them together and kind of play off the strengths of each. And I think that's worked really well. So now let me show you where these have gone. Next slide. They have been out in 6 hurricanes total. So we have sampled 6 hurricanes for a total of 72 buoys deployed. I think it's been across the board phenomenally successful. The first one we did was Hurricane Ian. And if you're watching the news, Hurricane Ian was a really destructive storm, and it was really made a big impacts, and it was our first one. So it was a difficult thing for us to do because we were still learning how to do all of this. But we did get a successful data set from this. If you look here, the inset is Florida, and then the larger view, the zoom view, is the coast of Florida. And you can see the track of the hurricane, and the numbers indicate the category of the hurricane as it was moving along that track. And then the different colored symbols and the little lines are the buoys that were deployed, and then they drifted along that little dark black track line. And then the buoy location is where it was when the hurricane actually came through. And you can see all the different buoy types there. And you can see that we sampled the Ian, but we only really sampled the left-hand side of the storm. So this was us still learning because the forecast was evolving rapidly, and the forecast, after we had made our decision, the forecast shifted to the right or to the east a little bit. And we wanted the storm to go right over the center of the array, but you can't tell a hurricane what to do. So it went a little bit to the right. You'll see, as Evan will now click through some later storms, we got a little better at this. In Idalia in 2023, that also hit Florida, the Big Bend region. We really nailed this one. We got a nice array out, lots of buoys, and the hurricane went right through the middle of the array. So now we can see what's happening on both sides of the storm, see the gradients and things that happen in these hurricanes. So this was really a big improvement in how we did the work in the deployment. Next. Hurricane Lee was much further offshore, but we decided to deploy for it anyway. That's a difficult set of decision making, whether you're going to spend all the money on the aircraft time and expend all these buoys based on a forecast. And Lee did not end up having enormous impacts, but it was still useful for us to forecast. And there was still some flooding on the Massachusetts and Maine coastlines there. So we put some buoys out for that. Now, Francine, at the beginning of this year, there was so much activity this year, you might have forgotten about Francine, but Francine came through the Gulf, hit the New Orleans area, and did have make some significant impacts there. Our array was a little bit off for that, although we did have the one buoy get completely run over exactly by the hurricane. So there was still some success there. And then Helene, which made a big deal in the news, and Francine after it. I'm sorry, Milton after it. And those were both really big storms with a lot of impact. And I think we did really well getting these sampled in terms of planning the array, looking at all the different forecast products that are available, working together almost always over the weekend because storms never show up during the weekday, and saying, okay, team, we're going to go for it. Here's when we're going to fly. Here's what the array should look like. Hey, we just got a forecast update. Let's shift everything to the east a little bit. Okay, that still looks good. All right, we're ready to go. Go time. It's a lot of real-time action to make this happen, but I think the team has worked together really well, and we've gotten good at it. We've gotten some nice results. So last slide from me is showing you a little teaser of what we've done with this. This is the work by Jake Davis, who's working on his PhD thesis right now. And he has shown us something that's long been hypothesized, which is that wave steepness, that's the vertical axis, as a function of wind speed, that's the horizontal axis, has some strange behaviors at high winds. The lower left part of this plot, we already know all about that steepness and winds go hand in hand, about linear together. And if it gets windier, the waves get steeper. No surprise there. But what we've been thinking happens is that at the very highest winds, you get to a limit of the steepness. You saturate in steepness. And this is probably related to the fact that every single wave is breaking. So every wave is at its limiting steepness, those highest winds. That's why the surface is just pure foam and spray. and it really changes how the atmosphere and ocean exchange at that point. So this is related to all the exchange of atmosphere and ocean. This is the first time we'll be able to have these kind of measurements. Jake's going one step forward of this and looking at how different it is on either side of the storm. So now we're looking at, in this panel, a storm following reference frame. The storm's in the middle, and everything, the data moves with the storm, and you can see that the blue symbols are in the right-hand side of the storm. That's typically thought of as the strong side or the dangerous side of the storm, if you're a mariner. And that side of the storm has even higher wave slopes than the other side of the storm because the wind and the waves are aligned on that side of the storm. So this is some of the science we're getting out of this. And this is the kind of stuff that's going to help improve our forecast because these wave processes have not been typically historically included in the forecast. So now we're using the wave information to understand a little better how the ocean and atmosphere talk to each other. Okay, with that, I'm going to hand off to Jenna now, and she can talk more about what happens when this stuff gets to the coast and the kind of impacts we see at the coast.
All right, thanks, Jim. As we go to the next slide, yeah, so my team's role in the project was to complement the measurements that Jim just described and relate those offshore forcings to the extremely dynamic surf zone and shoreline conditions by deploying sensors from land. And so for extreme storms, we want to be able to document the spatial variability in the height and timing, as well as the inland extent of the storm surge and waves along the impacted coastal areas. And so this requires distributing sensors along the forecasted impacted area ahead of a storm. We also want to improve our understanding of how storm-induced water levels and waves evolve within the nearshore and also then dissipate across natural and man-made landscapes. So in the pictures on the right, you can see the waves growing and breaking in the surf zone, and then the surge moving up the beach. And then in extreme cases, those surge and waves actually infiltrate the community behind the beach and cause infrastructure and damage inland. And so we want to deploy sensors across the beach to really be able to capture these physical processes during a storm. And ultimately, we want to use all these measurements to just validate storm impact forecasts and models from super complex 3D physics process-based models to more simplistic imperial forecasts that we can run quickly in real time. We're trying to collect data to really improve our understanding of all these conditions. And so to be able to rapidly deploy sensors ahead of a storm, we usually have 1 to 2 days before landfall. We have to get out to a lot of sites. So our approach is to utilize existing infrastructure to attach our sensors with the goal of really trying to get them as close to the open coast and shoreline as possible. So here we have a schematic of a beach profile and some pictures of where we might be able to opportunistically deploy sensors. The purple dots represent these pressure sensors that record internally, so they do have to be recovered after the storm to get the data. We try to mount these as close to the ground as possible. In some cases, there's jetties, so we can get those at maybe the shoreline position. Other beaches, there might just be a walkway or some kind of infrastructure at the dune toe that we can attach to. And a lot of times there's really no infrastructure on the open beach. So we'll put them on a power pole or something, you know, behind the beach and behind the dune. And at all the sites, we deploy atmospheric pressure sensors represented by the yellow triangle so that we can correct our water level measurements for barometric pressure conditions. And so this is kind of the extent of our sensors at our alongshore distributed sites, where we really just have to utilize whatever infrastructure is available. If you go to the next slide, we're trying to really increase our observations and make more detailed measurements extending out into the surf zone. So now in the schematic, I'm showing how we're utilizing pier infrastructure to attach these sensors. So we're still putting pressure sensors up the beach. On the bottom right, you can see attached to the walkway closer to the back of the dune. We're putting these pressure sensors on the pier pilings as deep as we can at the shoreline. You can see that at the bottom, second from the right. But what we're really doing with these transects is extending our measurements into the surf zone. So we're using non-contact radars that directly measure the water surface below the elevation, and we can compute surge, mean water levels and waves from these sensors. And so we'll put these at the midspan and the end of the pier. And these are actually recording and transmitting data in real time. So in the event that we lose a sensor, which unfortunately was the case during Helene, we still have all the data that's been collected up until that instrument failure. And so, so these non-contact sensors are really helping extend our observations offshore during storms. And so if you go to the next slide, this is an overview of all of our deployments for this project. So we responded to 6 storms in the last 3 years, deploying over 100 sensors total, with 2 to 10 technicians doing the deployments per storm. So a lot of work done by a few people in a little bit of time. And you can see the differences in our deployments depending on that time and availability, what our coverage is. And for all cases, our data is available on our USGS flood event viewer. And you can filter by storm, but I'm going to focus on our most successful deployment, which was for Hurricane Helene. So if you go to the next slide. This map is showing the distribution of our sensors. The purple dots are those bottom-mounted pressure sensors recording internally. We got those out at about 20 sites along the coast, both sides of landfall, which was shown there at about the Big Bend area. And we also had 2 crossshore transects deployed, one in Panama City Beach and one in Clearwater Beach, which are shown by the blue circles. And so that was great that we were able to bracket the location of landfall with those detailed transects. And so if you go to the next slide, we can look at some of our observations from our longshore coverage array here. These subplots starting at the bottom are our southernmost site in Venice. And then as you move up the plots, we're moving up along the coast to Panama City Beach. And these are time series. So the x-axis is time, the y-axis is water level in datum, so meters NAVD88. They're all relative to each other. And highlighting the time and the magnitude of the peak surge by the blue triangles. And so what we can see by looking at these plots is how we first noticed the peak surge at Venice, and then the magnitude of the surge increase as you move north along the coast, and the timing of the peak surge shifted in time. And so we noticed we had the maximum surge measured close to the landfall at the Dark Island and Fish Creek sites. And we also see from this data that the peak surge there was measured even before some of those sites in the embayed part of the Big Bend coastline. So, so these observations are really giving us an idea of the spatial extent and timing of the storm as it moved along the coast. And then if we go to the next slide, we can look at measurements from our detailed crossshore transects. So the inset pictures on the right are just showing a map view of those crossshore transects where we had pressure sensors at the back beach and the shoreline represented by purple, and the non-contact radars in the mid and end of the pier at both sites. And so in the figure, the plots on the left column is Panama City Beach, the right column is Clearwater Beach. The top plots are water levels, mean water levels, and the bottom plots are significant wave height. And the colored lines are just moving from darkest offshore to lightest onshore. And so really what we see is we can see some gradients in the water levels and the waves across the beach, and those do change with the storm as it approaches. And we can also see very obviously like the impacts were much bigger at Clearwater Beach on the right-hand side, the strong side of the storm, where we even our dune tow sensor was wet for during the peak of the storm there. And we're also able to measure waves with these sensors. And even though our wave radars went down during the Helene at Clearwater Beach, you can see those wave heights were ramping up, and our shoreline pressure sensor, we're able to measure over 1.5 meter waves at the coastline. So this was extremely intense, especially wave conditions, storm, caused a lot of destruction at the beach and inland. And so if you go to the next slide, we can just quickly look at how these observations can be used for model validation. This is a screenshot from a USGS total water level and coastal change forecast viewer, where all along the sandy coastlines of the Gulf and Atlantic, you can click a location like shown in the map there on the left. I've clicked on Clearwater Beach, and on the right, you can see the forecast water levels. This is for Helene. This is in collaboration with NOAA. They provide predictions of the mean water level, which includes the surge and predicted tides. That's the dashed blue line. And then we're adding a wave run-up component to that to get the total water level, and that's the solid blue line here. So in this instance, you can see the wave has a significant contribution to the total water level. And we're also comparing that to elevations of the beach and the dunes, and to get an idea of the amount of coastal change that we expect. And so on the bottom right, you can see a profile view where the total water level is predicted to be higher than the dune crest for a significant portion of the time, suggesting this site would experience inundation during the storm. And I'm just highlighting that the peak total water level we forecast was 3.2 meters. And so if you go to the next slide, we can try to validate this forecast. Sometimes, there's opportunistic cameras or other sensors nearby that can be used. So this series of photos is from a hotel, and you can see the Clearwater piers in the background, and you can see the water levels marching up the beach in time. And even that bottom picture, starting to see the water and the sand kind of infiltrate onto the walkway behind the beach. And so this storm actually made landfall during night, and so we don't have photos of the peak time of the storm, but that's where these sensor data is really valuable. So now on the bottom right, I'm showing the time series of our Clearwater shoreline sensor. And the blue line is the filtered surge data, and with the gray on top of it is unfiltered. So that's including the wave effects. And what we can see is our unfiltered maximum water levels were about 3.5 meters. So close to that 3.2 total water level that we forecast. So this would be great data to really validate our forecasts for the storm. And now I'll pass it over to Eric, who will describe a little bit of observations between the deep and the shore-based data. So thank you.
Thank you very much, Jenna. Yeah, I'm Eric Stackpole. I'm a mechanical engineer here at Sofar, and I helped to develop a lot of the air deployed systems that we made here. So I think I've got one of the coolest jobs. Like Evan mentioned before, we've got a worldwide network of free drifting and moored buoys. And I like to think of that kind of like a nervous system for the planet's oceans. So you can see on the left, we've got these surface spotters that are just free drifting. And we also have a version of those that are moored. And we have this system called Bristlemouth that allows us to talk through the mooring cable to attach other types of sensors. And that also allows us to have this capability at Sofar to build kind of bespoke systems, which we'll talk about more later, that use Bristlemouth to allow us to kind of rapidly develop new capabilities. So we adapted the buoys that we're already in the business of making for the NOPP program. You can see on the left and right the two airdrop systems. We also did use some moored systems, but I'm going to talk about the airdrop systems here. So this is our bread and butter buoy. It's called the spotter. It's a little bit bigger than a basketball. It weighs about 8 kilograms or 17 pounds. And it's got solar panels on the top, which allow it to run indefinitely. It's kind of got this weight on the bottom, which you can also attach sensors to. In the free drifting buoys, we have a temperature sensor there. And then on the top, there's a lid that protects this electronics box, or e-box as we call it. And that has a really good GPS that the system uses for tracking waves, satellite comms, compute, and a battery on board. If we were to do like an X-ray view of the system, you can kind of see what it looks like inside. There's this kind of black box in the middle. That's the e-box. And you can see all the wires from the solar panels and sensors and things are going into that system. So that's something that we needed to really reinforce in order to be able to throw these out of airplanes and have them survive. This is what a normal e-box looks like. You can see there's a wire that's just sort of plugged in, and you can already probably guess some of the kind of structural reinforcements that would be needed. We needed to make sure that those wires don't pop out on impact. This is hitting the water at over 100 miles an hour. Also, you can kind of see there's a split in the lower part of the box. That's where the battery is. The battery is very heavy and has a lot of inertia, so we needed to be able to reinforce that. We did a lot of testing to learn, what the failure modes were. But one of the things that I really like to point out about it, a lot of these things, even though we're doing this cool thing and dropping things out of airplanes, sometimes the simplest solution is the best. And that's certainly what we did with the spotters. You can see that to hold the battery in, we just use strapping tape, which has tremendous tensile strength, really good shear adhesion. It holds the battery in place. And then for the wires and things, we just use hot glue. It conforms to the shape of the plug. It's a very simple solution we could do quickly, easily, cheaply, and it worked great. Finally, we also noticed this really weird phenomena only through testing that the toggle switch in our e-box upon impact would sometimes switch itself to the off position. But again, that was a pretty simple solution. We just 3D printed this kind of interlock that goes over the system. And these things combined helped keep the system really strong. Another thing, if you kind of look at where that e-box is and how it's mounted, you can see it's kind of cantilevered. And I kind of made a more simple diagram here with my amazing MS Paint skills. You can see that because it's cantilevered, if it hits the water sideways, there's a lot of forces that are kind of being put on that flange. And one of the things we noticed on air drop testing was that actually the speed of impact didn't really matter. The spotter can be dropped from almost any altitude and its terminal velocity is survivable. But if it hits at an angle, that was what was killing things. So we needed to come up with a way to make sure that it would track in a straightforward way. You know, Jim mentioned also for their micro swifts, that's something they're very interested in. And we didn't want to use something complicated like a parachute that would need to be deployed. And what we came up with was another very simple idea. If you think of the shuttlecock on a badminton birdie, that keeps the badminton birdie pointing into the direction it's traveling. And we were able to use very simple means, once again, literally cardboard and tape, to basically make a shuttlecock for the spotters. And this is just pieces of cardboard. They're trapezoidal pieces of cardboard that wrap around the perimeter of the spotter. Spotter happily has these kind of corners that are able to stick out through those holes in the cardboard that holds it in place. And we also noticed that that system, because it's so simple, can be easily folded up and put in the same packaging as a normal spotter. And this simple solution has allowed us to not only use it for these systems, but also other government agencies and research groups are already starting to use this for their own work outside of the NOPP program. So we were able to commercialize this very simple solution that you basically just strap onto a normal spotter, and it works. So here's a quick GIF of what that looks like coming out of an airplane. You can see it tracks. This is a Cessna 172 or a 182 that we use for airdrop testing. It hits the water at full speed. There's a big splash. And another thing that's really nice that we kind of learned about is that the cardboard on that impact breaks into smithereens and ends up, you know, just floating separately. And what you end up with is this spotter buoy that's basically the same as if you had gone out in a boat and placed it in the water, even though you threw it out in an airplane. So the other system that we built, this was kind of my baby that I really enjoyed working on over the last 18 months, was the submersible spotter. You can kind of see it on the right. And you know, like I said, it was only 18 months from the initial concept of this coming together to having deployable systems. And the way we were able to do that so quickly was with this Bristlemouth connectivity standard that I've been talking about. Basically, Bristlemouth allows you to connect marine electronics very easily. So we took a normal spotter e-box and popped that in a new enclosure. And then we took one of the sensors that we already use in our smart mooring system, and it just plugged right in. So being able to kind of rapidly integrate these electronics allowed us to focus more on the hardware aspect of this. The idea of the submersible spotter is that it has to be thrown from an airplane, hit the water, sink to the bottom, take measurements with this pressure sensor, which is used to measure water height, and then after some time, about 5 or 6 days, pop back up to the surface and relay its data, which I'll show you more about later. So you can kind of see how the system is put together. On the top, you have this e-box enclosure, which is an air-filled pressure-proof container that holds the e-box, and it also, all that air adds buoyancy, it adds flotation. And then in the middle section, we have this really fancy pressure sensor built by RBR. It's high resolution, and that allows us to take these, you know, centimeter level accuracy measurements of water height from the bottom. And at the bottom, there's an anchor, which keeps the system anchored against the seafloor, and this galvanic time release I'll show you later that slowly dissolves away and eventually releases it from the bottom. And you can see what they look like on the right. So I mentioned this galvanic release. Here's kind of another MS Paint drawing. You can see this gray box. That's what this looks like. And now let's see, we're letting the slide load. All right, there we go. So basically, it's a metal system that has 2 dissimilar metals. And it's not loading. It's all right. I'll show you what this looks like. So the way it works is we throw this system out of an airplane. And it hits the water. And once it hits the water, it sinks to the bottom. And then the pressure sensor measures the height of the water. And then as the storm comes, that's kind of, think if you blew into a shallow puddle that would push a lot of water forward, that's what the storm surge is. It's measuring that with the pressure sensor. and it's recording all this data in an onboard system in the e-box. And then once the storm has cleared, that galvanic timed release, which looks kind of like this, these two pieces of metal, slowly corrodes away. And so you can see over time, it's getting thinner and thinner, and eventually that allows the floating portion of the system to pop back up to the surface, where it relays its data via satellite. So here's what the system looks like. It's basically just these tubes. We've added a little cardboard collar that allows it to track well. And you can see as it gets thrown out of the airplane, it just goes straight down, and it even plunges through the water. You can kind of see it dart in. And so I wanted to show you kind of what Jim and Jenna have been talking about, what it's like when we do a deployment. So basically, you know, about a week ahead of time, we'll start getting, you know, predictions that a storm may hit the US. We'll be looking at these. We'll start a Slack thread and kind of start talking about it. Usually about a day or two beforehand, we'll actually get the green light of like, okay, this is definitely happening. We're going to deploy. So we'll fly to Pax River Naval Air Station in Maryland. We'll do a pre-flight brief early in the morning. You can see we're looking at these maps that are showing where we want to deploy the buoys, making sure we are straight with all that. The air crew also has this information on their GPS systems, so they'll know exactly where to drop everything. And I've created this video, which will play now, that kind of gives you a sense of what a day in the life is. So it starts early in the morning. We're loading all of our systems up in this truck that'll go to the P3 Orion we're going to use. Getting onto the plane is really neat. You know, this is not like a commercial plane. You'll see inside it's really spacious. We just have all of our buoys piled up there on the ground, ready for deployment. And then it's time for takeoff. So, you know, we take off pretty early. It's going to be, I think, on the order of like a 5-hour flight down there, 4 or 5 hours. And we're flying over the US. This is for Helene. Eventually we get to our drop site over the water. At first we're at high altitude, where we're going to be dropping the drifters and the micro swifts. And you can see it's really just kind of hanging out. There's not many seats to sleep in or anything. I spent a lot of the flight standing, but it starts getting really exciting as we're getting ready to deploy. So first off, you know, we're arming these drifter systems. You can see there's this tape that's removed. Those are getting thrown out this sonobuoy tube you can see to the right. And then this is one of the micro swifts. It's really simple to deploy these. All you do is you just line up with this tube and pop it out, and that's what it looks like. Then we went down to a lower altitude, and like Jim pointed out, you know, the spotter buoys we have are larger, so we have to throw them out the side door. So we open this door up. You can see everyone's harnessed up, so you can't fall out of the airplane. We also have this safety bar, and then you see he's going to tap on her shoulder 3 times. That's the pilot via communications radioing 3, 2, 1, drop, and that's the exact spot that we're dropping on. I got to do this myself. This is my helmet cam. This is a submersible spotter, and it's a 50-pound system, so you know it takes some heft to lift. And you can't see it, but he's tapping on my shoulder. 1, 2, 3, go, and out it goes. This is my first time dropping this after working on it for 18 months, so it was kind of high fives all around. And you know, after this whole day of deploying these, it's already nighttime. You can kind of see some thunderstorms in the distance. We head back. I think this ended up being something like a 10-hour or 10.5-hour long flight there and back. But we deployed, you know, many buoys, I think well over 20, and we ended up getting some great data back. And let's see. So, right, you know, what does this all mean? You know, why are we doing this? It's exciting to deploy these, but you know, what we're focused on is impact. You know, first off, we showed that it's possible. You know, we deployed in 6 major hurricanes, over 50 systems were deployed successfully. We noticed in one instance a 70-foot wave height in a hurricane. And by the way, that's all visible on our publicly available dashboard. You can go to weather.sofarocean.com and you can see the live data coming from these buoys. So people were watching that real time. And one of our submersible spotters, which sank to the bottom and then popped up afterward, was able to relay data to show us that there was a 2-meter wave height measurement predicted over what the predicted, or measured over what the predicted tidal response would be. So we're getting really interesting data that's unprecedented. It's never been collected before. Also, you know, government agencies and coastal communities have really been able to use this to predict and prepare better for storms through a partnership with the National Mesonet Program, Synoptic, and KDR. we were able to make this data available to the National Hurricane Center, which is the leading authority on extreme storm forecasting. And NHC was able to validate their weather models, which is really important, and verify conditions real time. We were able to make short-term adjustments to wave forecasts, enhance situational awareness, and early warning systems. Someone from the NHC, you can see the quote on the bottom, said, we're seeing these spotters tonight and using them in analysis already. That was as the storm was happening. And that's really what this is all about. It's about making unique data that has real impact on forecasts that can help protect lives and property. So it's been an incredible project to work on. And I think with that, I'll pause and we can open it for questions.
Great. Thanks so much, Jim, Jenna, and Eric. We have time for questions. So I'll get those loaded up. Let's start for a question for Jim. Can you describe a bit more what factors you consider? How do you make decisions around the exact drop locations for systems ahead of the storm? What goes into that?
I think the number one thing that goes into it is really what's the track of the hurricane, what's the forecast track, and what's the uncertainty in that. There are lots of different forecast systems running both operationally and on the research side. So we have some sense of a cone of where the hurricane is going to be, and we certainly want to capture that. And then we tend to bias a little bit towards the right-hand side of the storm. As I mentioned earlier, that's typically the stronger winds, the stronger impact, more storm surge, all those effects. But we don't just want that. We want to capture both sides of the storm because there's a lot of interesting physics between the two. And with this goal of improving forecasts, we want to observe the whole thing. We want the synoptic view of the whole storm, which again is something we have not historically had with our previous approaches to this, where you just have a handful of buoys out there moored at kind of arbitrary points. So our targeted arrays, they try to capture both sides of the storm, the whole storm. And then the last thing we think about is we think about the human factor. We think about the infrastructure of the coast. Where do people live? Where are the population centers? And we should certainly be covering that and making sure that we have the data that's going to help us inform and understand, what happens in that part of the coast. And so one example would be for the Big Bend of Florida. That's pretty sparsely populated. So during some of the storms that were headed there, we still ended up with buoys down, towards Clearwater and towards the rest of Florida to make sure we're covering that. Jenna, Eric, you want to add anything on
that? Jenna, you shared work that was focused a lot on shorelines and cross-shore transects. We're curious, when we think about combining those with the more offshore buoy data, what does that do when we combine those data sets, or what might that do next for some of the work that you're focused on?
Yeah, I think, that's still research to be looked at. This successful deployments this year, we now have these coincident data sets with offshore wave conditions, and then looking at the timing of those impacts reaching shore. And that's what the key component of these non-contact radars that are on the piers are helpful with, is that as soon as those are installed and turned on, we're measuring the water surface. So we're measuring the calm conditions before the storm, and then we're really measuring the intensity and the ramp up as those offshore waves that Jim's buoys are measuring start to reach the shore. And so typically with these pressure sensors deployed on land, we have to wait till they get wet to know what's happening. And so that's the beauty in these cross-shore transects. And so now we have these coincident data sets in time that we can really start comparing when we're seeing those conditions from offshore reach land. So
great.
Yeah.
We have a couple. Oh yeah, go ahead. Cool. We have a couple questions on the spotter air deployment system that I can take. So yes, we do have it's commercially available. So we have a commercialized version of the system that Eric talked about for being able to deploy a spotter from a airplane without any parachute. We don't have a commercially available system that is the submersible spotter. And yes, our intent is that as much of that cardboard foil is degradable as possible. There are some elements in the tape that aren't degradable, but we're working on replacing those with purely degradable elements that'll fall off on impact and harmlessly biodegrade in the ocean. And then a question, Eric, what were some of the major lessons learned from the early air deployment trials? You mentioned we had this 0 to 18 months we were deploying systems at scale. What were some of the big lessons learned along the way? And maybe you can talk about when we started the process of actually testing these things in drops.
Yeah, totally. It was a really cool project with a lot of iteration. That was really important to us. You know, when we started out, we did plan to actually have these systems parachute down. We had a static line parachute system developed, but actually through a few anomalies as we were testing with the parachutes, where they released from the parachute early or something. We noticed that they were surviving as long as they, like I talked about before, as long as they impacted straight up. So that was a change that we made that was really great. It made the system more simple. The other thing we noticed is those galvanic timed releases that I mentioned. If they get embedded in a lot of sediment, which you can expect happens as a hurricane passes over, the sediment caking around that part that's supposed to corrode would cause it to take a lot longer to release. And so in some cases, if the buoy doesn't pop up when it's supposed to, it's because of that. So these are all kind of lessons learned that have kind of helped us as we look forward to how to make these systems work better. And it's funny, we're talking about hurricanes and things. There was a hurricane or an earthquake recently here, and we're getting tsunami warnings now here in California. So hopefully we'll be okay.
All right. Marcos is going to be joining us at BristleCon next month. There is a developer conference for Bristlemouth, what Eric mentioned, and also has some ideas for using spotters in audio-visual spaces, which I'm excited to hear about at BristleCon, Marcos, so come find us and say hi. For a question both for Jim and Jenna, maybe Jim, you can start. Can you describe some of the other projects that you're aware of or collaborated with in the NOPP program?
Yeah, so this NOPP program is large. It has more than just the team you see here and these observations here. It also has a set of different teams working on improving forecasts, particularly for the coastal flooding and the coastal damage. And having been in this business for a while, I've been really excited to see just how far they're taking that. They really are taking it not just in the forecast sense of the weather and the geophysical forecast, but all the way towards what damage will occur at individual structures. And will that damage be critical damage that means the structure, the house, the building is gone forever, or it can be repaired, it can be replaced. That kind of level of fidelity on almost a house by house basis, which is amazing because they're reaching into these national inventories of structures and the really end for end kind of forecasting from all the details of the hurricane to will that house be flooded and be beyond repair, that kind of thing. And it's been great to have a diverse set of teams doing that. So not just one forecast system, but a couple different forecast systems that are, in a friendly way, sort of competing with each other to say, well, in this storm, this forecast system really performed well, and this other one had less skill. And then in a different set of conditions, this system has more skill. So let's take the best from each of these things. And a couple other things I would highlight are that there's really a new awareness about the importance of vegetation, that if you have a vegetated dune or a feature like that, that can really change the amount of inundation, the amount of flooding. And that's something the entire coastal engineering community is really, rallying around in lately. And so it's neat to see that getting into these models. In addition to the infrastructure, we're also talking about, what is the surrounding environment as a natural environment or as something that's been, maybe it's been, recently redeveloped in some way. And so we're really looking at that to improve the forecast.
Great. Jenna, are there any projects that you're aware of from the NOPP program that you want to mention?
No, just building on what Jim said, there were also groups trying to utilize satellite imagery and remote sensing to measure flooding extents and other hurricane parameters. And Jim touched on building the digital elevation models that are the basis for these models and the different components that they can provide that improve those storm forecasts. And then not necessarily a NOPP project, but similar, a collaborative project that occurred several years ago now called DUNEX during a nearshore event, extreme event, where an opposite approach where all kinds of researchers agreed on a location to deploy sensors over the course of several storm seasons to try to measure storm impacts. And so you can imagine there's some differences in the way that you measure and the results that you get, but that was another kind of extreme storm project that we've been able to learn a lot from too. So, yeah.
All right. A question for Eric. Can you describe the lifespan of the spotters that are deployed? Are they recovered? Do they last forever off of solar power? What does that look like after the storm has passed?
Yeah, no, it's super cool. I mean, for the surface spotters that we deployed, after they hit the water and are used in a hurricane, they become the free drifting spotters that are part of our network. So right now, if you log on to weather.sofarocean.com and look at all the buoys that we have around the world, you'll see that there are a bunch in the Gulf, and those are buoys that were actually deployed by airplanes for these hurricanes, and now they're feeding into our larger network of systems that's doing other measurements. So they keep on being used, for many years. And I know, Evan, you're familiar with how a lot of those go too. But I think that's a really cool aspect. And then as for the submersible spotters, a lot of those they have labels in them of how to contact us, and eventually a lot of them drift to shore. We've had people contact us when they wash up, and we have those people send them back to us, and we can reuse the parts and things like that.
Great. And another question for both Jenna and Jim. This might be a tough one to answer on the spot. What is the most interesting or notable or surprising kind of individual observation that you recall seeing from this program? Are there any like really surprising errors that we measured against the forecast, or new unexpected measurements?
Jim, you can go ahead. My most impressive measurement was actually from one of the buoys deployed offshore that I think Jim mentioned measured over 10-meter waves on the Gulf Coast of Florida. From our observations, we're still digging into the actual what we've measured and comparing with models and all that. I do think Milton was interesting for us. We deployed on both sides of landfall. So the weak and the strong side. And as I mentioned, if you don't have a sensor that's wet all the time, you don't know what's happening. And so it was really interesting. All of our pressure sensors north of landfall didn't measure anything, which was representative of this drawdown in the water level that we could see at a NOAA station. And so what looks to be no data is actually an indication of this drawdown on the weak side of the storm. And then, of course, we saw really increased water levels on the strong side. So but yeah, still tons to dig into for us.
Great. Jim?
I think I'll just add that, these big waves, I mean, it's always phenomenal to see big waves, right? I think the biggest HSIG we saw was 13.5 or 6, so 13 meters, right? These are very big waves, and that's HSIG. So within that wave field, there's probably something that's twice that before it's really a rogue. And there's huge waves. Well, what's amazing to me is, most of these buoys report every 30 minutes-ish. And how fast those statistics change as a fast-moving hurricane with these dramatic winds comes through. So if the buoys that get run over direct hit by the hurricane, they will go from a significant wave height that is 5 meters to 8 meters to 13, then back to 10 to 9 to 5 to 2. And just the rapid adjustment of the sea state is really remarkable. It's fascinating. I think there's still quite a bit to learn there in how we forecast that, because there's a whole bunch of sort of quasi steady state assumptions in the way we set up these wave forecasts, and those kind of rapid changes are surely violating a few of those things.
Well, this is interesting, but we actually have to evacuate our waterfront office due to the tsunami warning. So I'll collect the last set of questions and comments in the chat, which is passing on a lot of thanks to Jenna and Jim and Eric for the work that we're doing. We have people who were directly impacted by Katrina, people thanking Jenna for putting sensors on existing infrastructure to get missing real-time data. So thank you all, and thanks for joining the webinar. And we'll post updates to let you all know that we're all right. So yeah, a good one.
Stay safe. If we know anything from these programs, you evacuate when they say evacuate. Go.
Yep.